Hey, this is Mr. Ariel. I'm here today with the first lesson on electron configuration. Now, to put a fine point on it, electrons are extremely important for a lot of things we have to learn about this year, and the arrangement or the configuration of how they go around the atom is really important. So let's get into that. Now, in an earlier lesson, I think we learned about the Rutherford model. That's the one where Rutherford had figured out that the center of the atom had protons and neutrons, and he also knew that electrons were orbiting around the nucleus. He also determined that the vast majority of an atom's volume was made up of the electron cloud. Now, I'm not expecting you to get this into your notes right now. We learned this previously. Let's move on. Now, definitely get this part into your notes. We've already learned about the Bohr model of the atom, but we need to add some to the idea. Bohr's atomic model was an update to Rutherford, but he suggested that atoms existed in specific orbits around the nucleus. You can see here in the picture that this atom has 11 electrons, but they're arranged in 3 orbits, starting with the first, closest to the nucleus, and then counting out from there. Make sure you've got this idea of orbits and energy levels into your notes, because I need to move on. Now, you might be wondering, how did scientists figure out that the electrons are arranged in these levels around the nucleus? I mean, atoms are incredibly small, so it's not like you can put one under a microscope and see all this on your own. It turns out there is something else that you can see with your eyes, and it's light. And it was used to figure out how electrons are arranged around atoms. First up, some background information. Make sure you're getting this into your note. I have a massively blown up atom here in the corner. It's not even close to scale. So we've got just one electron orbiting the nucleus. Remember that electrons have an opposite charge from protons, and so that makes the nucleus here positively charged. And so this electron is strongly attracted towards the nucleus. But it doesn't fall in because it's orbiting around the nucleus just like the moon orbits around the Earth. Now, if this atom is heated up, this electron will gain energy. Energy is just the ability to cause change, and the change that occurs to this atom is that electron is going to get boosted up to a higher energy level. Let me draw that in. Let me drag it up here to the second level. All right, now that this electron has been boosted up to the second energy level, it's gained energy, and so we call it the excited state because it has that extra energy in it. Now, you might be saying to yourself, how do scientists know that this happened because electrons are really too small to see? Well, if you're asking that question, you have the makings of a great scientist. After all, scientists are skeptical of everything, and they really want to see the proof. And that proof better be excellent if it's going to become part of science. So how do they know this happened to the electron? Well, that excited electron doesn't stay there very long. Very quickly, it loses that energy and falls back to the energy level that it came from. So let me drag it back down here. And so we're no longer in the excited state, we're back to where we came from, and so that's called the ground state. Now, when this electron falls from the excited state and back to the ground state, this energy is given off as light, and that's something we can see with our own eyes. Here you can see a video of some copper being burned, and it turns the normally yellow flame to a distinct green color. Now, when you see things like green fireworks, that green color is produced because the explosive itself contains copper, and every element, in fact, gives off its own unique pattern of light. Now, I forgot to mention one thing when I was going over the notes here. This little flash of light is called a quanta. And so I'm going to add that in as the name that you need to get into your notes. Focus on getting everything on the board into your notes because I need to move on. Now, don't worry about getting this into your notes. I just wanted you to have a little background information. Scientists use a device called a spectroscope, and this is a really simple one set up here. It's a light source, and this part in the middle is a card with a very thin slit cut into the middle, and then we have a prism on the other side. And what happens is that white light approaches the card, a tiny bit of it passes through the card, and then as it passes through the prism will separate it into all the colors of light, something like this. Now let me show you this in action with a real element. Here you can see it's kind of a reverse. The light bulb is over here, there's the card, and then here's the prism, and here you can make out this pattern of light. Now this bulb over here looks a little bit weird because it's an old kind of fluorescent that you don't see much anymore, but it actually contains mercury. That's Hg on the periodic table. And so the light produced by fluorescent bulbs always produces this color pattern when it's broken apart using a spectroscope. And you can think of this part over here as being like a signature for an element, because each element produces its own unique pattern. Now, moving on a bit, here's an image of the light signature that's given off by lots of different elements. Every one is totally unique, and that's because the electrons are arranged in a unique way around each atom. Thinking back to the notes we already had, each one of these color lines is caused by one of those excited electrons falling back to its ground state and releasing that energy as light. Now, getting back to some ideas you do need in your notes, scientists measured the wavelength of each band of light. If you look at a model of a wave, and it kind of looks like this, wavelength is this distance from one wave crest to the next. And it's abbreviated with the Greek letter lambda. I think it looks kind of like a little wave crashing onto the beach. So scientists measured that wavelength, and then they used an equation to work out the frequency of each light wave. It says that the speed of light, c, is equal to the wavelength multiplied by a wave's frequency. Frequency is the number of waves that pass by a point in 1 second. Now, you don't have to know where this equation came from for now. It's actually from physics, and we don't have a lot of time to learn about that in this class. Now, from this point where we know frequency, scientists can use another equation to determine the energy of the wave. And that equation states that energy is equal to a number called Planck's constant multiplied by frequency. Now, this equation right here is from a really complicated area of physics, and so we don't have to learn anything about where it came from or why the equation works the way it does. The end result is you can measure the wavelength of this quanta of light and then figure out the amount of energy that's being given off by those electrons dropping back to their ground state. Now, remembering that each electron shell around the nucleus is called an energy level, this is where scientists proved that the electrons are actually arranged or stacked up in different levels. Here's the nucleus, and that electron on that first energy level got boosted up to the excited state, and then it fell back to the ground state and gave off light. And so those light signatures with all the bars of color on them, if you think about it being like a graph, we have the ground state at the bottom, and then each bar of light that's given off represents a certain amount of energy that's being given off as those electrons fall back. Now, if this electron fell back to the first energy level, it could be boosted up again, but this time it might gain enough energy to go up to the third energy level. And if that were to happen, it would fall back to the ground state, but it would emit a totally different color of light, and that would be recorded on that color signature. Remember, each band of light represents the different amount of energy that the electrons have gained. Now, scientists noticed on those light signatures that there was nothing in between the different colors. It wasn't a smooth transition, they're distinct bars. And so from that, they worked out that each bar represents an energy level. Now, this subject can get really complex from here, but we don't need any of those details for this class. Right now, if you've got the basic ideas into your notes, you're all set. I hope this video has been helpful to you today, and as always, thanks for watching.